I think we're making really good on time. Remember, in this course, we only deal with three primary topics: ANOVA, which we did earlier, regression, and then we get to the third topic in the course, and that's all. We only deal with three basic courses. I'm sorry, three basic subjects in this particular course. So I did leave you hanging a little bit from last week, and let me see. This was. I'm not going to show it. As a matter of fact, yeah, I'm not even going to show that. But you remember from last class, I gave you a definition for coefficient of multiple determination. We're going to go a little further with that today, and but I'm just going to use this data set that I mentioned to you guys on today. Hopefully, everybody had a chance to perform the regression on the Glencove data. You may not have seen that message that you were taking the quiz, but we're going to be focusing on that data set today. So if you haven't already, open a data set that says glencove.xls, Excel file, and perform a regression on that. When you're trying to predict the appraised value of a home. I'm going to try to share this here. Okay, here it comes. You're trying to predict the appraised value of a home. You see that first column there, and the handout that goes, you open that is the handout right above it. It says something like R squared and beyond. That's where this data kind of is coming from. So we're going to have to answer questions regarding this particular data set that's based on that particular handout. So if you open up the handout, you'll read, we're trying to, for example, predict the appraised value of a home using three explanatory variables. Now, up until this time, we've only really dealt with two of them, like foot traffic and minutes open or something like that from the extra handout. But there was nothing that says you can't have more than two explanatory variables. So in this case here, you may have to zoom in a little bit. In this case here, we have three explanatory variables. And if I had to label these, the appraised value would be Y, land acres would be like X1, age would be X2, and rooms would be X3. I got this data set from somewhere, and actually in the real data set, it was actually six. It was like 6X values, but I just got rid of three of them. Right, so there is no limit as to how many X variables you can have. I think the ones I got rid of was like number of bedroom. Oh, no, that's here. I forget what the other three were that I got. In this case, we have three X values, and we're trying to see how they relate to appraised value. Okay, so I did the regression. Take a look, and I put my results over on the right. See if your results match mine. Question?
Professor, every time I try to perform the regression, Excel comes up with an error message saying there's a problem with the formula.
Okay, so when you do it, you have to highlight appraised value as your Y, along with the words appraised value. So you have to make sure you include the words appraised value.
Yeah, I have that highlighted, saying not trying to type a formula when the first character is an equal or minus sign. Excel thinks it's a formula.
Right, so that means you have to check off where it says labels.
I have that checked off.
Right, so you're gonna have to do it like this. I can go over it really fast, real fast. Okay, so when we go over here, what you want to do is check data, and everybody else, if you're lost, follow me, please. Data, and go to data analysis. There. We have regression, press OK. So what you want to do in the Y column, make sure the cursor is right there. Make sure you highlight appraised value, all these values right here. I don't know if you guys can see this, but do appraised value all the way to the bottom, 221. Now put the cursor inside of input X range. Now what you want to do is highlight all three of those columns there, including the words, land acres, age, and rooms. all the way down to the bottom. Again, make sure, I don't know if, can you guys see? Okay, yeah, I'm not sharing my screen, so you can't really see the, okay, yeah. So hopefully you guys see my screen. So when you do the input range, you have to make sure, again, you're highlighting the words, land, acres, age, and rooms, all the way down to the bottom. Make sure you're checking this thing that says labels. And when you output range, you're going to choose somewhere where you want your data to appear. You're going to make sure it's clicking inside of here. And I make sure my data appears somewhere over on the right-hand side, in this case here. You should need, when you press OK, then the results should pop up. Overwrite existing data. Okay. Everybody okay?
Thank you.
Okay. All right, so one thing I left you guys hanging on, and I'll answer that question in just a second. One thing I left you guys hanging on last week was, stop sharing here, what the meaning of R squared is. So I'm going to, if you look here, you see this, what is your value for R squared here? Are you guys getting is that 0.67, 0.677? I'm looking at the top. You guys have that same R squared value?
Yes.
Okay, so what I'm going to do, I'm going to pick up where I left off last week and write how you would summarize what the coefficient of multiple determination means in this particular problem. So just hold that question just for a second and write this on, I'm going to write on the board, and this would be how you would interpret the coefficient of multiple determination in this particular problem. Say something like, in this problem, so this is coefficient of multiple determination. Coefficient of multiple determination, which is still R squared. But I just want to make sure we knew how to write it in the case when you have more than one X variable. So we say something like this. In this case, solution, we say 67.7%. I just changed that to a decimal. 67, am I recording? Yeah, 67.7% of the variation in appraisal values. See, now we have a totally different data set. This is talking about appraisal values, but this is my Y. So, you know, it's the percent of the variation in Y, in this case, our Y is appraisal values, is explained by the variation. Okay, so this is 67.7% of the variation in appraisal values is explained by the variation in the set of, is explained by the variation in the set of the three, explained by the variation in the set of the three explanatory variables. Now, I'm just not going to write what those variables are, but if I really want it to be precise, I would say is explained by the variation in what are those three variables? Number of bedrooms, land acres, and whatever that third one is on Excel. So it's three variables, explanatory variables. So the only difference between how you say it here and simple linear regression, in simple linear regression, we're only listing whatever that one variable is because you only have one x variable anyway. The only difference is I just have to say explained by the set of variables in a particular case. So somebody asked a question earlier first. Who is that? What was the question?
That was me, Professor. I did the regression for the data analysis, and I have the same numbers as you, but my decimals are in different places. Because I use the appraised values all the way on the right-hand side. Does that matter?
You should be using the data that's all jumbled up. Your y should be basically 1,000 times the values all the way over on the right. That's why I put them all the way over there. Don't do those. Don't do those. Okay.
Professor, can you read it? What the board says?
Yeah. So it says 67.7% of the variation in appraisal values is explained by the variation in the set of the three explanatory variables. The set of the three explanatory variables. So that just kind of ties up that loose end from last week. In other words, we're going to go a little further today because you see how this number is not really close to 100, 67.7. So, you know, the closer it is to 100, then the better the line is in predicting. So now we're getting into situations here where it's not, I mean, it's an okay predictor of appraisal values, like these three variables. But how do I know? Eventually, we're going to talk about how do I know which variables are weak and which variables are strong that contribute toward that 67.7%. Because see, this only tells us how the group is acting, right? Well, yeah, I do have a dark one, but that's I think it's because of how I'm kind of positioned on the board. But I'll try to use black in the future. But that one also, that marker color is also fading. But we'll see how it goes. We'll see how it goes. Okay, so here's what we want to look at now. There are two things we need to get through today. One of them is looking at how strong your model is in predicting. Okay, so make sure you have the Excel file that you just did there, and I'm going to introduce it this way. Suppose, okay, so we have three x variables, right? X1, x2, x3. Land acres, number of rooms, and whatever the other one is. Okay. How do you know? I'm going to throw this out there. How do you know which model is better at predicting appraised values? Okay, well, what do you mean which one is better? I only see one model. And when I say model, I'm just, for example, when I use the word model, okay, so this is starting out okay. Hopefully the color holds up. When I say model, in this case, for example, my model will look like y sub L equals M1 x1 plus M2 x2 plus M3 x3 plus B. Now you can look at the results there, and we can figure out what M1 is, M2 is, what M3 is, and what B is. And that was like the first problem in the quiz, right? So what I'm doing, calling this a model, right? This is a regression equation, and it's a model that we're using to predict. Now, say for example, I want to look at different arrangements of this model that has different values for K. You say, what is K? Okay, just follow me along. Follow along. See if this makes sense before I write any definition. Do you agree that another model that can come out of this looks like this? Y sub L equals M1 x1 plus M2 x2 plus B. You say, well, where's the M3? Well, I didn't use it. In other words, I could also analyze appraised value only using 2 of the 3 x variables, right? Because it may be that I get a better prediction just using 2 of the values rather than all 3. Here's another. So this is model 1. This is model 2. You probably could figure out what model 3 would look like. Oh, I don't know. Let's see. What's another possibility? See, this marker's just happening. What's another possibility? Out of the different arrangements, because I have M1, then I have M2. What's another possibility? M what? What's another possibility of ways?
M1.
M what?
M1.
M1, X1, and then what? Plus. Now, the thing about, now remember we're dealing with multiple regression. So I have to stay away from examples where I'm only using one of these, because that's implemented regression. So I have to have at least 2 examples that I'm thinking about. So I can also have M1, X1, and then what? And what?
M3.
M3. M3, X3, then plus B, leaving the X2 out. Does anybody see one last one?
M2 and M3.
Good, very good. I know this is a different way of thinking, but you just follow me. Just follow me. Now, this is the original one, based on how many pieces of X variables or how many X data points we have altogether, right? But it may be the case when I compare these models, I may end up with different R-squared values. What does that tell me? What that tells me then is, depending on this arrangement, or this arrangement, or this arrangement, or this arrangement, I could get a higher R-squared value, which means those values are better at predicting a raised value. Get that? Okay. Now, notice here, I want to say k equals 3. What do I mean by k? K is going to be the number of explanatory variables I'm considering. See, this x1, x2, that's x3. So I'm going to say k is equal to 3. So I don't want you to confuse this. Remember, in ANOVA, we also had k, where k was the number of groups that you had. But in this case, our k is just going to equal the number of explanatory variables that I have. What is k here in model 2? K is what? What explanatory variables do we have in this case?
2.
Good. K is also 2 here, and k is also 2 here. Why did I just point that out? Because, okay, here we go. Here we go. We're approaching what we need to know for the first thing. If I am trying to compare different models that have the same k, so act like model 1 is not there, because the k here is 3. If I want to compare the results of different models in terms of the to see if they're good at predicting y, appraised value. Yeah, this is k equals 2, k equals 2, k equals 2. What I do is run separate regressions, just using these 2, then using those 2, then using these 2, and compare the R-squared values. Okay, I'm more that in a second, but I want to show you what's going on here. So in other words, imagine model 1 is not there. You see how k equals 2, k equals 2, k equals 2 here? So it's almost like comparing apples to apples, right? I've run a separate regression just using these 2, then these 2, then these 2. Then I look at the R-squared values, whichever one gives me the highest value, then that's telling me that model is better at predicting appraised values. But look at here. Look at here. This here is k equals 3. What do I do if I want to compare models when the k's are different? If I bring 1 back into the mix, here k equals 3, here's k equals 2, k equals 2, k equals 2. As soon as these values right here become different, I cannot use r squared when comparing them to each other. I've got to use something called adjusted r squared. You're going to find that in your printout. So what I want to do is write this definition. You write this for me, and we're going to go back and actually solve this problem. Because number 1 on the handout is asking for something quite interesting. So I'm going to say definition. I'm going to say the adjusted. You guys can let me know if this marker is a little bit better. The adjusted r squared statistic helps us to compare. Okay, so this says the adjusted r squared statistic helps us to compare models, M-O-D-E-L-S, when, oh boy, the number, it helps us to compare models when the number of x variables, when the number of x variables in a group differs. Okay? It says when the number of x variables in a group differs. Okay? We determine which of the arrangements gives us the highest percentage. Okay, so we're going to actually do this. We determine which of the arrangements, and all those different arrangements that I just erased, these are the different arrangements that comes out of having those 3 variables. Which one gives us the highest percentage? Now we've done a regression already on all 3 variables. That's without staring you in the face. So now what we want to do is, in this case, do 3 more regressions. But when you do them, so I erased it, but model 2, that with x1 and x2. What is x1 and x2 in this problem? Compare models when the number of x variables in a group differs, period. Number in a group differs, period. Then say we determine which of the arrangements gives us the highest percentage. Okay.
Thank you.
So here, yeah, sure. Here's what I want you to do. What is x1? X1 is land acres, right? What is x2 in this problem?
Age.
Age. So what I want you to do now, given what you know, run a regression, but this time don't highlight all 3 x variables. Only highlight so y is still going to be the same, appraised values, but just highlight the first 2 columns and do a separate printout just for those. Or not printout, but find the results for those. If you can put them on the same page, or if you want to go to another sheet, just those on a whole nother sheet in terms of the results. So do that one. So what you're doing, you're going through all of the different arrangements that comes out of those 3 variables. So you have x1, x2, then you're going to do another one that has x2, x3. which is age and rooms, I think. And the last one is going to be X1, X3. And that may be a problem doing that last one, so we may have to talk about it. It may give error. I want to make sure everybody understands what we're doing. And then we'll take a break in a minute. I'm going to try to share my screen and try to do Loom, but it hasn't proven. Let's see. Okay, I'm going to try this. Then I'm going to try this. I hope this works. I don't know if I'm popping up in so we already have this results right here. What I'm going to do, I'm going to do 3 more regressions. The last one may be tough, but that's regression. Okay. The Y is still going to be the same, but I'm just going to adjust input range to do the first 2. I'm going to make mine just put it on another sheet as opposed. I don't know. You can put all yours on one. I'm going to do a new worksheet. Okay, so that's that one. Then I'm going to do another one with just age and rooms. Age and rooms. And I'm going to put that on a whole nother sheet. And then finally, the last one we have, I don't know, they don't have to be in order, but the last one has to be land acres and rooms. So you see how you're skipping over the age? Did anybody figure out how to do land acres and rooms? Did anybody get a result for that? It's like you have to skip over age. What did you do?
So I highlighted land acres, and then I did like not the semicolon, the other one, the ones where it's just 2 like periods over, like if you do the shift semicolon button, and then I highlighted rooms, and then it was able to work. But I'm not sure if like it still gave.
Oh, so in other words, you kind of highlight and then held shift and then highlighted the other column.
Yeah.
Okay, so let's see. So if you guys are wondering, let's see, I'm going to do data analysis, regression. I'm going to clear this out right here. I'm going to clear this thing out for X range. And I'm going to highlight land acres with the words. While that's highlighted, let's see, if I do shift, hold shift, and then room, no. I have an easier solution, but I'm trying to see. Okay, land acres, which is here. You have shift and what now? Let me see.
I didn't hit, like I hit the land acres, and then I hit and then I pressed colon to put in after I hit so I highlight land acres. And then after that, I hit the colon. I put in colon after the range.
Okay.
And then I highlighted the rooms, yeah.
Oops. So something like that.
Yes.
Okay. Let me see something. And then those of you who can't understand what we just did, I'm going to see if I do another solution. Oh, okay. Well, see, now here is still giving me land, acres, land, age, and rooms. I only want, in your data, did it only give you the 2 that you were looking for? Because colon in Excel means through. So if it still, did it only give you land and rooms?
No, yeah, Give me all three now, I see.
All right. I have a different way, and unless somebody else, let's see, who is this? Yes, so go ahead, whoever that is.
Professor, I just copied the acres row and then I copied the rooms row like somewhere else on the sheet
Yeah.
next to each other, and that's how I did it, and it worked fine.
Yeah. So in other words, because you're going to find out with Excel, it really has problems skipping columns. So what you can do is literally pick up the first column, put it somewhere on the right, and then pick up that third column and put it also on the right so that they're right beside each other. So something like this. Let me find my data. Okay, so I'm going to pick up land acres. I'm going to do copy, paste. Then I'm going to pick up rooms, copy, paste. So now they're right beside each other, right? So you don't have to worry about trying to figure out how to skip over and then do a regression just on those. So we have data analysis, regression. So here what I'm going to do, and then just clear out this input X range. That's going to be the same Y. Then for the X range here, for this one, just hide right beside each other. In Excel, it's called being contiguous, right beside each other. If you do that, it should only give you the land acres and the rooms as your answer. Let me know in the chat if you have all of these different arrangements. So we different answers. We should have the first one that we did with all three. Then you should have one for like x1, x2, x2, x3, and then x1, x3. Yeah. We're going to come back and finish this. And while we're doing the break, I'll work with some of you individually to see what the problem is. Now, so this, so here, I'm going to look here. This is the very first one that we did. Notice here, it has all three X values, X1, X2, X3, namely land, age, and rooms. The second one we have shows results for, see here, land acres and age. The next one, age and rooms. And then the last one, land and rooms. So we have 4 different pieces of results that we're going to consider. So we're the handout. We're on number 2, I think, where it's saying using the following 3 independent variables to determine which variables. It says k is greater than or equal to 2. I think we talked about that. 2 k equals 2 just means you have 2 independent variables. Greater than 2 is 3 in this case. We'll never use k equals 1. Because remember, k equals 1 is just simple linear regression with just one x value. So it says, hint, you will need to run 4 different regressions, which we just did during the break. You'll run one regression with all of the variables. And the other regressions are like subsets of variables that have x1, x2, x2, x3, then x1, x3. Okay, so look at your results. Look at the results we have. Hopefully, we have 4 different sets of results. And I wrote this here on the board so you can kind of see what we have here. I wrote model 1, 2, 3, 4. Now, this first model is when you're looking at all of the independent variables. So this says k equals 3. We're dealing with x1, x2, and x3. Model 2 is when we're dealing with like land acres and age, I think, then age and rooms, and then land acres and rooms, right? So these are the different ones we're looking at. Now, let's go to our results. Let's look at the first one that we, the first results that we have there. I don't know if you can see it, but see if you can locate the thing that says adjusted R squared. It should be right up on the R squared.
Professor, for number 1 in the worksheet, did we find an answer for that? Like, is the regression line a good predictor of appraised values for homes?
I don't think we did that. So let's see, number 1. if you guys, okay, so if we look at number one, so we are not comparing across groups. So when we're not comparing across groups where these Ks are different, which value on here answers the question for number one? Is the line a good predictor? Which statistic on here just answers that basic question? Does anybody know?
0.64.
So we're going to use the 0.64 eventually for number two, but for number one, which do I have to look at?
0.67.
Right, just the regular R squared. So the regular R squared, and so let me say this. So the regular R squared is what we're just what we would use. We just want to know, just in general, is this line or is this regression line a good line to predict? Notice I'm not comparing anything, or right. Okay, so it essentially number one will kind of be what we wrote already. 67.7% of the data is blah 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 blah. What we wrote earlier when we were talking about the coefficient of multiple determination. So I asked myself, is 67.7%, is it close to 100%? So remember, the closer it gets to 100, then the better that looks predicting. So the way I would answer one is this line a good predictor? I would say it's a fair predictor, right? And what are you using to make that conclusion for number one? You're using just the regular R squared, just the regular R squared. So you can say it's a fair predictor. So when am I using R squared? I'm using R squared one of two times. When I just want to answer the question as to whether that line itself is a good line to predict, or watch this, and I kind of alluded to it earlier, or I am comparing this model to that model, but my K's are the same. See that? See K equals 2, K equals 2, K equals 2. If those were the comparisons that I'm comparing, then I don't use adjusted R squared. I could use the regular multiple R squared, R squared. In these cases right here, and then I can use those to compare. But as soon as I introduce this one where K is different, see K equals 3, 2, 2, 2, then that's when I have to use the adjusted R squared. All right. So tell me, what is the adjusted R squared value as a percentage for number one? And I think somebody told me already. What was that adjusted R squared for the first model? 60 what? 60 what percent? Go where it says adjusted R squared for the first model.
64.
64 point what? We'll go one decimal place. Is it 0.7?
Hold on, let me look.
Let's see here. So this is the first result, 64. Can't see. Oh, I guess 0.0. 64.0. So 64%. Now go to the results when we did x1, x2. Tell me, what is that adjusted R squared? So this may be on a different sheet. What is the so this is, what is the adjusted R squared for land, acres, and age?
55.
Is it 55? 55%. Do you guys see what we're looking at? I'm not sharing my screen, but each one of these models, you're going to the results and you're going up to the top where it says adjusted R squared and telling me what that value is. Okay, how about the next model? When we're dealing with, I guess, x2, x3, what is that adjusted R squared?
39.8.
39.8.
The value is 0.3977, so I'm assuming it's 39.8.
Okay, all right. You just move the decimal twice to the right.
Yeah.
Finally, what's the last one? So this one will be back to like do the separate columns. We have to sort of make them into their two separate columns. What is this? Land and what was the last one? Land and rooms. What's that one?
43.3.
43.3.
Do you want, when we're finding these adjusted R-squareds, do you want decimal places or no? Because if you want them, the first two would have a decimal place as well.
Well, yeah, but I think the first two, I think the decimal is 0. So I think that's why I didn't write it.
Yeah, okay.
It is 0. It's 0. But yeah, so in general, one decimal place is fine. One decimal place. If it's a 0, you don't have to worry about writing it. Okay, is everybody understanding like where we are here? We really didn't do anything. The biggest in using adjusted R squared is just, do you know how to make the results appear? Okay. So what's our conclusion? What's our conclusion? What did it ask? What does the question ask? And what is our conclusion? Which variables yield the best prediction for a home's appraisal value? So now we have this competition going on. What do you think?
Model 1, because it has the highest adjusted R-squared.
Very good. Very good. So I'm going to erase this and kind of write the conclusion. So we're trying to see which of these model arrangements yields the best prediction. And we're going to say results of something like the variables of land acres. Well, I guess land, I forget what it was, whatever that title is. Land, age, and rooms yield the best prediction. Okay, so it says the variables of land, age, and rooms yield the best prediction for a home's appraisal value since it has the highest, okay, since it has the highest, it's kind of fading out. Adjusted, since it has the highest adjusted R squared value, then in parentheses, just put what that value was. I think it was 60, I think it was 64%, something like that. I'm gonna write it like this actually. R squared, and then adjusted equals 64%. So this is R squared, and then sort of like as a subscript, like in the bottom, I'm saying ADA adjusted. Let you know that it's not just the regular R squared equals 64%. Okay? Now, I don't want us to always think that the case when you have all of the variables, this will happen, and this is x1, x2, x3. See here, the reason I listed those there, land, age, and rooms. See, that represents k equals 3. If the highest adjusted R squared would have been like the last one, then I would only write those two words right here that correspond to the columns that they came from. So it's not all the time going to be the case where all three variables or all variables are going to always give you the best prediction. You have to do the separate regressions, and you have to make your conclusion based on that.
Can you
Michael,
move the board because I can't see it at all?
Okay, it says the variables of land, age, and rooms yield the best prediction. Yield the best prediction for a home's appraisal value Since it has the highest adjusted R squared value, since it has the highest adjusted R squared value, and it says R squared adjusted equals 64%. Generally, the higher the percentage is, of course, then the better the line is in predicting. Okay? Questions?
Wait, what was the last part that you just read?
Since it has the highest adjusted R squared value, it's 64%. Look at page 336 in the textbook. Now, there's a formula for R squared adjusted at the bottom of the page. This is just the tweaking of R squared in terms of how to calculate it. But, I'm not going to ask you to calculate that. If I do like extra credit, that's not a big deal. Notice how inside of the formula, there's an R squared. That's just a regular R squared. And then it's adjusted based on the model that you're looking at. Look at page 338. 338. This is similar to the table that we just did here. You can kind of see they have model 1, model 2, model 3, and they have the different arrangements that are going on, the different values for K, and then the different values for R squared adjusted. Notice that we exhausted all possible arrangements. For example, if you have 3 variables to start off with, then you have to go through every single possible arrangement leading up to that 3. So we did these two, these two, these two, and then finally all 3. Imagine the hell you will go through if you have 4 variables. Because you have to go through all the ones with 2s, all the ones with 3s, and then finally all the ones leading up to 4. Now, of course, I won't do you like that, unless it's like extra credit or something. But really, if you think about it, it's not hard, it's just tedious. Because you have to go do this one in Excel, then that one in Excel, then that one in Excel, and then and compare all these adjusted R squares. Okay, but I would never torture you like that unless it's like extra credit or something like that. Okay, and any questions about what we did in terms of figuring out how to figure out the best prediction when the K's are different? So just let me explain. If I'm only considering, if I tell you only to consider just situations where K's were similar or equal or the same, I would still just use regular R squared. But as soon as I start comparing when the K's are different, I have to make sure I use adjusted R squared.
K's are always given, right?
K's, well, when the original K is given, if I tell you to consider these 3 X values, X1, X2, X3, then I know that K is 3 from Jump Street, right? But what I have to do is do all the ones leading up to that 3, right? So if K is 2, what are the different arrangements where I can have K as 2? The first 2, the next 2, and then these 2 over here. So K is given in terms of the ceiling number or the upward number. Then I just have to make sure I do all the ones leading up to that. Like we did K equals 2, K equals 2, K equals 2. Now I don't do K equals 1 again, because again, that's just regular simple linear regression. But I always let you know how many X variables you're dealing with in that problem.
Okay, that makes sense.
All right.